now we will start with the displacement field. Now this displacement field meaning u x as a function of x comma y, u y as a function of x comma y. This displacement field looks similar to what we had considered earlier, but of course slightly different. For example, both u x and u y are functions of x and y. Okay. You have both x 1 I appearing both in u x and u y also, and earlier we had only alpha and beta, we had delta also. These are chosen so that to demonstrate certain features or demonstrate that the total displacement can be split into its components, that is the idea. Okay. So, displacement field is chosen to demonstrate that the total displacement is sum of the deformation plus the rigid body rotation. Okay. Now, let us calculate all the 4 gradients, okay, which will be useful for us. So, dou u x by dou x, which means differentiating the first the x component dou u x by dou x, you get alpha, the value of alpha is 0.04. Then differentiate dou u x with respect to y, you get beta plus delta, and if you sum these two you get 0.15. Next, take the y component, differentiate that with respect to x, you get minus beta and that is minus 0.05. Take u y, differentiate with respect to y, you get 2 alpha which is 0.08. So, this we will keep it handy so that we can use it very as we go along. We are given the displacement field and we have calculated all the 4 displacement gradients. Once again, what does this displacement field represent? You have a plate and then it is subjected to some force, and this displacement tells you displacement of all the points in the plate. Okay. And this displacement includes all the components, we are going to separate each of them. Okay, first let us look at the total displacement. Okay. We are going to arrive at total displacement in 2 different ways as we have done in the derivation. First in terms of the partial derivatives more mathematically, second in terms of splitting each of the components. Okay. So, the first method total displacement. So, we are going to look at difference in displacement. Okay. As we have discussed, difference in displacement takes care of translation. Okay. Now, how do you write total difference in displacement between 2 points separated by delta x delta y? What are the points, any 2 points in this plate? Okay. We write it as, if in the x direction, du x as dou u x by dou x dx plus dou u x by dou y dy. This is writing this is using the first method where you express the total differential in terms of partial differentials. Now, I will write in terms of delta for easy understanding. Okay. So, delta u x equal to dou u x by dou x delta x dou u x by dou y delta y. Now, in the particular case the displacement field is linear, they are all functions of x y, not x squared y squared or x into y, which means that our displacement gradients are constants. Remember we had values 0.04, 0.5, 0.8 or whatever value, which means they are constant throughout the plate. Okay. So, displacement field is linear, so displacement gradients are constants. So, now let us consider points A and C. I will demonstrate all for point C, then you can extend to other points. Consider points A and C because they are delta x, let us say delta x, this is delta x, this is delta y, distance away. Okay. Now, in the particular case A is not displaced, so the total difference in displacement becomes total displacement of point C. Okay. We actually supposed to consider difference in displacement between C and A, but because A is not getting displaced, the difference in displacement between C and A becomes displacement of C itself, in this case total displacement of C. So, A is not displaced, so total difference in displacement becomes total displacement of point C. Okay. So, we will talk in terms of displacement itself. Okay. So, coordinate further the coordinates of A are 0 comma 0. So, delta x delta y becomes x and then y. So, the second expression just becomes simplified in this way. Okay. Why is it simplified? Left hand side is difference in displacement, we just now said it becomes equivalent to just displacement. So, I am writing it as u x, and the right hand side we have delta x and delta y, because coordinates of A are 0 comma 0, they become just x comma x and then y. Okay. This is what we will use for further. Similarly, we will use later on also. So, what we have done is started with the total difference in displacement in terms of the partial derivatives, and then delta x delta y. Difference in displacement becomes displacement because one point does not move. So, for all the conditions we will take A as our reference point, and so that becomes easy to understand because A does not get displaced. So, the left hand side becomes just u x. One more simplification happens because coordinates of A are 0 comma 0, delta x delta y becomes x and then y. Okay. Okay. Now, we will calculate u x is equal to dou u x by dou x x plus dou x by dou y y, okay. Simplified version of the general expression. Similarly, we can write for u y also, okay. Just like we wrote for u x, I have written for u y, and we will take all the values which we calculated for all the gradients. Okay. We calculated all the combinations of the gradients. So, we are the components of the displacement gradient tensor more formally. Okay. So, now for point C, which is 1 comma 1, total displacement, okay, u x is equal to 0.19 and u y is 0.03. How do I calculate? Take this expression, okay. You know dou u x by dou x is 0.04, this value is 0.04, and dou u x by dou y is 0.15, okay, 0.15, x is 1, y is 1, giving you u x as 0.19. Coming to u y, dou u y by dou x is minus 0.05 and dou u y by dou y is 0.08, x and y are once again 1 because we are calculating for point C, and so you get 0.03. Okay. This is what is shown in the diagram here. As usual, the red boundary shows the initial configuration, initial state, and the coordinates are 0 comma 0 etc., and the blue boundary shows the final state. Remember, the final state shows the displacement of all the points. We have calculated for C alone. If you repeat for all other points, you can get the coordinates of B, coordinates of D, then you will be able to draw the boundary of the plate A, B, C, D in the final state. Now, remember, it shows the total displacement. This displacement could be because of rotation, normal strain, shear strain, okay. And this is what we are going to do now. Separately represent normal strain, shear strain and rotation, sum up and see that we will be able to get back this total displacement, and that is what we did analytically, but now we are going to do in terms of a numerical calculation. Okay. Okay, so, coordinates of C in deformed configuration due to displacement, you know the displacement. So, just add to the original coordinate. Original coordinate is 1 and the displacement is 0.19. So, 1.19, and the similarly in the y direction 1 plus 0.03 1.03, and that is what is shown here. It is 1.19 almost 1.2 and this 1.03 slightly above 1. Okay. So, those are the coordinates. Similarly, you can calculate for A, B, C, D. Okay. Now, what we will do, take normal strain alone, shear strain alone, rotation alone, and see how the displacement happens. Okay. For the when we consider normal strain only, the difference in displacement or the differential displacement is equal to epsilon x x into delta x, and that is what is written here. Du x is equal to dou u x by dou x into dx, and as usual, as we have discussed earlier, difference in displacement becomes displacement, delta x becomes x, and so we get this simple expression. Similarly, in the y direction, we write du y is equal to dou u y by dou y into dy. How did we write that? For the normal strain only, the difference in y displacement is given by epsilon y y into delta y. Epsilon y y is nothing but dou u y by dou y into dy. So, as we have seen earlier, we get this expression for displacement. Okay. So, we will take all the values of displacement gradients from the first previous slide. So, that now we can calculate for point C. Once again I take point C. What is this called? Displacement due to normal strain only. Okay. Ux is equal to 0.04. Why is that? Ux is dou ux by dou x, which is 0.04. Straight away the value is here. What is, of course x is 1, okay. And what is uy? Dou uy by dou y, and that value is here as 0.08 into 1 is 0.08. Okay. And what are the coordinates of C in deformed configuration? Due to normal strain only. Look at the statement, coordinates of C in deformed configuration due to normal strain only. Add the displacements to the respective old coordinates, you get 1.04, 1.08, and that is what is shown here. C, the x coordinate is 1.04 and the y coordinate 1.08. Similarly, you can calculate for other points, and the red boundary becomes the blue boundary. This displacement is because of normal strain only. Okay. Now, let us proceed to displacement due to shear strain only, okay, which means that we have to consider the second column. Now, dux is equal to epsilon x y into delta y. Remember, epsilon x y is gamma x y by 2, and this expression for gamma x y multiplied by half into dy, and like in the earlier case we write this as ux is equal to these sum of these derivatives into y. And similarly, in the y direction we take this expression epsilon x y, it is same, okay, and uy is equal to gamma x y by 2 into x. Here epsilon x y into delta y, here epsilon x y and delta x. So, what you have here is y here and x, otherwise these two are same, this term and this term are same, both are epsilon x y. Okay, now, let us get all the values of the gradients from the previous slides. Other two gradients are here. Okay, so, now for point C, which is 1 comma 1, displacement due to shear strain only. Okay. How do you calculate? Ux is dou uy by dou x plus the other terms, dou uy by dou x is minus 0.05, and then you have dou ux by dou y, which is plus 0.15. When you sum up, you get 0.1. When you divide by 2, you get 0.05. Okay. So, if you want to write here minus 0.05 and then you have 0.15, sum divide by 2, you get 0.05. Multiply by 1, of course results in 0.05. Same for uy also, because this epsilon x y is same for both of them. Multiply by x, x is equal to 1 here. This need not be, this will not be the case for points B and D, because there x and y are different. Because it is point C, x and y are same, so you get the same 0.05 here. So, now what are the coordinates of C in deformed configuration due to shear strain only? Okay. Just add to the original coordinate 1 plus 0.05, 1.05 both for x coordinate and y coordinate, and that is what you see here, 1.05 and 1.05. Of course, clearly only the shear strain is present, and that is what we considered. Okay, now, last one, displacement due to rotation only. So, we should consider this column, the third column. What is the expression? the difference in displacement is equal to minus omega xy into delta y, that is what is written here. This is omega xy multiplied by minus and delta y or dy. As we have done earlier, left hand side becomes ux, right hand side becomes just y. Let us write down for dy from this entry in the table, which is just plus omega xy. So, this is omega xy, okay, including half, it is omega xy, okay, multiplied by dx. So, once again this becomes uy, right hand side becomes x. So, now let us get all the derivatives. That is why we calculated all these derivatives to begin with. Okay. So, we require that several times, and so it becomes handy to calculate and keep it ready. Okay. So, once again for point C, displacement due to rotation only, ux is equal to 0.1, uy is equal to minus 0.1. So, how do you calculate? Dou uy by dou x is minus 0.05, okay, and then you have dou ux by dou y which is plus 0.15, but you have minus here. So, and then if you add these two, you get minus 0.2 divide by 2 minus 0.1, and then you have another minus here the outside. So, you get 0.1. Of course, multiply by 1, that anyway is 1, gives you same result. For uy, it is minus of the above expression, x is still 1. So, you get minus 0.1. So, now let us add to the original coordinates of C in deformed configuration due to rotation only. Just want to mention, it says deformed configuration, but says rotation only, looks little paradox, because we said deformation is normal strain, shear strain only, but this is the usual nomenclature used: initial configuration, final configuration, initial state, final state. Okay. So, that is why this says deformed configuration, meaning final state, the blue boundary, due to rotation only. So, add to the original coordinates, you get 1.1 and then 0.9, and that is what is shown here. Just the element as rotated, can calculate for other points as well. So, the x coordinate is away from 1, that is 1.1, and which means it has displaced to the right, and the y coordinate is 0.9, it has got displaced down, and that is why it is below 1. Okay. And so, the only rotation has been considered. Okay. So, now what is that we have done? We have separately considered the displacement due to normal strain, shear strain and rotation. Now, it is time for us to put them together and check whether we get the same as we have done straight away with total displacement. So, let us do that. That is what is shown here. Okay. Now, we will discuss for point C. Okay. Point C, displacement due to normal strain only. The values were 0.04 and 0.08. Okay. The corresponding figures are shown here, the bottom of the slide. The first figure shows for normal strain only, and the displacements were 0.04 and 0.08. Okay. That is also seen here. Now, next we considered shear strain only. So, displacement due to shear strain only is shown in this diagram, and the displacements were 0.05 and 0.05. Remember, we are listing down displacements, not the coordinates. What is shown here are the coordinates, what is listed here are the displacements. So, 0.05 and 0.05. And thirdly, we took displacement due to rotation only, and the displacements were 0.1 and then minus 0.1, and that is what you see here in this diagram. Now, let us add all the displacements. Coordinates should not be added, anyway that is not meaningful, displacements have to be added. So, sum of displacements, which means that sum all these displacements along the x direction, sum all these displacements along the y direction, you get 0.19 and 0.03. Now, what is the coordinates of C in deformed configuration due to sum of displacements? 1.19, 1.03, and that is what is shown here, which is same as what we got earlier by straight away writing total displacement, okay, and that is what is shown here, okay, of course same as that obtained from total displacement, and this is what is shown in larger sized figures. This shows the previous slide where the individual displacements are shown, okay, in the x and y direction, and the sum is also shown here. This large figure has been obtained two times. First, by considering only total displacement in terms of partial derivatives, which is more mathematical. We got the coordinate of C as 1.19, 1.03. Now, these individual figures are considering normal strain only, shear strain only, rotation only. When you sum up all the displacements, once again you get the left hand side figure, but now by decomposing the total displacement, splitting that into components because of normal strain, shear strain and rotation only. So, a good example to visualize what we mean by representing a displacement gradient tensor as sum of strain tensor plus a rotation tensor. Okay. And just to like to mention about this coordinate C, of course obvious, look at this, if you look at start with the normal strain, there is positive x displacement, and due to shear strain also there is positive x displacement, due to rotation also positive displacement. That is why all of them get added and you have a large positive displacement, a total displacement. Now, if you look at y displacement, it is positive y displacement here, here again a positive y displacement, but when you come here rotation, there is a negative displacement in the y direction. That is why when you sum up 0.08, 0.05 minus 0.1, you get a small positive y displacement. That is why if you look at initial C and final C, large x displacement and a small y displacement. Okay. Of course, that explains whatever I discussed earlier little more graphically. Okay. Okay. So, now we can write this statement again, that the displacement gradient tensor is sum of two tensors. Okay. Now, I think we can look at it more physically, geometrically, instead of just looking at in terms of calculus or differentials. Okay. And remember, that is why in the end of the previous discussion, we were looking at the physical significance of these terms. Okay. We said dou ux by dou x initially was just a mathematical gradient, slowly we said see it represents normal strain, and then we said these two sum together represents shear strain, and we said that will lead to the present discussion, and that is what we have done now. These two terms put together represents all the displacement due to the normal and shear strain, which we call as deformation. The second tensor is of course the components due to rotation. Okay. So, let us symmetric tensor, anti-symmetric tensor we have seen, and the strain deformation tensor, rotation tensor. You need not even discuss in terms of tensor, just understand in terms of matrix, easy for understanding. Okay. And of course, we said displacement as translation and rotation, rigid body motion, this kind of summarizes what we have been telling so far. Okay. Displacement because of translation and rotation, which is rigid body motion, a normal sign shear strain, which is deformation. Okay. Now, kept as a kind of suspense, why did we really split into two parts? Okay. And that answer that will be answered now. Now, if you take a plate and then apply a force and just let us say translates, obviously there will not be any internal stress, it just rotates, there will not be any internal stress. But now let us say you try to pull, then there is internal stress, which means that there is a change in length, the strain and the stress are related. Try to squeeze in, what happens? The shear strain and stress are related. Okay. Other example would be, if I just move, I am translating, no, I do not feel any stress inside. If I just rotate, I do not feel any stress. Of course, if I keep rotating, I may feel giddy and fall, but that does not mean internal stresses are developed. but imagine somebody is trying to pull me this side, pulling me that side, really I will be in severe stress, and that is what exactly is happening. So, physically intuitively we can understand, more mathematically also we can say, physically we can see that the stress is related to the strain part only, but not to translation and rotation. Translation we have taken care, but we have to take care of rotation. That is why we separated, see this tensor on the left hand side includes rotation, normal strain, shear strain. Based on the discussion, the stress is not to be related to the rotation. So, we will have to take out this rotation part, and that is what we have done now. So, the important tensor for us, or the important components for us, are the components of the strain tensor, not that of the rotation tensor. Okay. Just one more point, we are right now discussing a strain for solids. We have discussed stress, and we are going to relate these two, okay, and that we will see of course later. So, let us complete whatever I said. Rigid body motion bracket translation and rotation is not related to stress. Okay. Deformation bracket normal strain and shear strain is only related to stress, okay, and hence strain tensor, not displacement gradient tensor, related to stress tensor. How are we going to relate, that we will see, but we should be ready with the right hand side. Left hand side is stress tensor, the right hand side is the not the displacement gradient tensor, but the strain tensor, components of that. Okay. So, relate stress tensor to displacement. When I say displacement, it is displacement gradient, not even displacement gradient tensor, but the one part of it, namely strain tensor. Okay. That is the biggest takeaway from this slide. We have, I said I will tell the motivation later. Now, it becomes very the motivation becomes very clear now, that is why has been reserved till this point, that the reason for splitting is the only one part of the displacement gradient tensor is to be related to stress. Okay. And in terms of our journey to the Navier-Stokes, we were here ready with the linear momentum balance for fluid, and we found out that the viscous stress tensor is unknown. We need to relate it to the velocity gradients, and we said to understand velocity gradients we will take a diversion to solid mechanics, and first we understood normal strain, shear strain, rotation, displacement gradient, and now we understood this particular block which says differential displacement is equal to the deformation plus rotation. The reason is that this deformation or the strain tensor alone is important for us to relate to stress. Okay. So, in terms of the plan, now that we have discussed all the concepts of solid mechanics, understood the displacement gradient, now it is time for us to go to fluid mechanics, discuss these two blocks, and we will see how all these concepts analogously apply for the case of fluids. What is our objective? To relate the viscous stresses to velocity gradient. Understand velocity gradient, we came to solid mechanics, discuss displacement gradient. We go to fluid mechanics and discuss about velocity gradient, and then we will have to relate these two. Okay. That is what we do here, where we relate stress to the strain and go to fluid mechanics and relate stress to strain rate. What is strain rate we will understand later. Okay. So, when we say stress strain relationship, it is between stress and the strain tensor. Okay. Of course, that we will understand as we go along, just to give you a outline at this point. Okay. So, let us summarize this part of the lecture alone. The components of displacement are translation and rotation, which you call as rigid body motion, normal and shear strain, which you call as deformation. Okay. And the displacement gradient tensor we have seen as a sum of strain tensor and rotation tensor. Only the deformation part of displacement is related to stress. Okay. Relate stress tensor to strain tensor, which we will take little later, meaning going back to fluid mechanics and when we come back to solid mechanics for the third time we will do this, but now we are going back to fluid mechanics in the next lecture to discuss about velocity gradients. All the concepts discussed for solid mechanics you will see that analogously can be applied for fluid mechanics. Of course, small concepts are there that we will discuss.